you, Charles. I think mostly that I really like using them and I want to use them a lot. And then Charles did everything for me. So, Charles. And Michael coming up with all the derivatives and things that have. So there's an HMM functionality in command stand if you didn't know. So you don't need to write out the entire forward algorithm. There's a lot of great functionalities. But thank you for being here. I know it's 9 a.m. I hear there were some coffee shop lines that made it hard to get the coffee. So, coffee on me later on if you'd like. I could go for a second one. So today, from the depths to the stars, how modeling shark movements illuminates star behavior. And yes, there's going to be sharks and there's going to be stars. So this is one of my first times giving a keynote, and I never know what to do. Do I give a 45-minute talk on one thing? And I was like, well, I've done a lot of little things, so breaking it up into 3 different parts and kind of what you can take away from each section. So shark movements and hidden Markov models. Basically, you too can become a shark statistician if you would like. My journey in going Bayesian and interdisciplinary research. And from the ocean depths to the Milky Way stars, working with sharks is another route to becoming an astrostatistician. So I don't know why I got the Fresh Prince of Bel-Air song stuck in my head when I was thinking about my journey, but I felt like a little out of place, and you kind of show up and you're like, what's going on? So I was thinking like, this is a story all about how my life got flipped, turned upside down, studying math and sharks, as you do. And these are actually some of the sharks data that I work with. These are leopard sharks in Catalina Island in California, and there's so much data. But you can see the leopard sharks, they're smaller and they like to hang out with one another. And the reason I was able to do statistics and work with sharks and do all these things, because my formation is I have an undergraduate degree in math, I have a PhD in statistics. I've never done any ecology. So maybe that's one myth that you think, like, if to do interdisciplinary research, you need to know this domain. I just have a shark obsession. I knew a lot about sharks, and I knew some math, right? So, but there's this area called ecological statistics, which back in the day, we really talked about it being an interaction between statistics and ecology. Nowadays, there are computer scientists, mathematicians, physicists, engineering. Physicists are coming up with these incredible models of the energetic budgets for different sharks. How many squid do they need to eat per day, for example? And in the UK, I've been quite jealous because there is a National Center for Statistical Ecology, for those who may not be aware. I started on the left, statistics. There's a lot of people that start on the right, ecology. And you can either call it ecological statistics or statistical ecology. It doesn't really matter. You get there either way. And the question is always, well, how much statistics do I need in order to be a statistical ecologist? How much ecology do you need to be an ecological statistician? And I'm very much coming from, I do a lot of interdisciplinary work. My formation was very disciplinary, but now I tend to do a lot of work across fields. And I would say all you need to do is be committed to learning how to speak the same language. So as long as you're committed to saying, okay, here's what the tail means to me. What does a tail mean to you? Right? Because sometimes we'll talk about a tail and they're like, yes, the shark's tail. I was like, no, not the shark's tail. The tail of the distribution. Right? It happens more than you would think. So as long as you're committed, to kind of learning and embracing and being in a room with people that you're like, I have no idea what they're talking about, but eventually you will. You can also be interdisciplinary. Animal movement. So I started working in animal movement about 10 years ago now. And there was this great paper that came out in Science 2 years ago. Big data approaches lead to an increased understanding of the ecology of animal movement. Basically, there is so much data being collected now. Right? So there are these incredible satellites, especially in Europe and the UK. You have a lot of people working in this area, a lot of people with incredible data. New satellites that are being used to collect data as well. And they highlighted what's called hidden Markov modeling. So this is an example from the paper. This is oceanic white-tip shark data collected by my colleague, Dr. Vianey Papastamatiu. And basically, my journey has sort of been, I really liked math. I got into a PhD in statistics, and I said, what can I do to work with shark scientists? I really like state space models. I thought they were cool. I got really good at learning about hidden Markov models, and then realized that they're really useful in animal movement. So this only came out 2 years ago, but 10 years ago I started my journey with hidden Markov models in animal movement. So as you saw yesterday, there's already, I think, 2 talks at least talk explicitly about hidden Markov models. You have an observation process, Y. This is what you observe. So with the animals, we can observe their position. And it could also be, like if you have a smartwatch, it can observe what you're doing now. It doesn't know that you're sitting or you're resting, but it's saying that, well, you're not really moving, right? So those would be the observations that we can record from animals. And we have the state process, which is some latent thing that we don't see. So if you have a smartwatch on right now and it's trying to infer what you're doing or how much energy you're expending, it doesn't see you sitting. It just records different processes and is likely going to infer that you're resting, so you're not burning more calories. Right? So I wanted to get into some basics for those who may not know what a hidden Markov model is. It's a doubly stochastic process. In its most basic form, it assumes conditional independence between the observations. And this is why here we don't have the arrows between the Ys. Now, the fun thing with these models is you can just start sticking arrows everywhere, right? You can add all the arrows you want. But in its very, very basic form, it does assume this conditional independence. The state process is assumed to be a first-order Markov chain. So what occurs at time t depends on everything that occurred previously only through time t minus 1. And the observations are generated according to a set of state-dependent distributions, which is the terminology I use. Can also be referred to as emission distributions. Essentially, like right now, if you're sitting, what kind of movement patterns would you produce if you were sitting? And I see some of you kind of like shifting right to left. Some of you are just very still. Some of you have your hand like this. There's all these different patterns and movements that you're doing as you're sitting. So I don't know how many of you are coming from a more statistics department or that training, but statisticians and a lot of people don't believe me when I say you don't need to use what's called the complete data likelihood, which means you don't need to have a function of the state process as well as the parameters. So
Vianey, isn't Z usually on the left there? For the complete data likelihood?
Yeah, I guess, sorry, yes, Z on the left. Yes, sorry, Z on the left, and when you do inference, you usually alternate between parameter estimation and state estimation. So sorry about that. So yeah, Z on the left. So the idea is that they think you have to do the parameters and the state estimation simultaneously. And that's kind of prevalent across a lot of fields. You can't fit that model in STAN because the states, at least in a discrete time finite state HMM, are discrete. Right? So you can't take gradients, but you can evaluate the likelihood. And you can marginalize, you can take the sum over all possible state sequences in a very efficient manner called the forward algorithm. And part of it is let's go back. This likelihood is actually a matrix product. And like I think Connor said yesterday, you do the forward algorithm evaluation one step at a time. Right? So anyway, you don't have to know all these details. It's just only you have to use the second one to fit an HMM in STAN. That's it. And also, it's possible to do this. There's different application categories for HMMs, and this is also covered in the STAN manual, which is fantastic. There's the sort of fully unsupervised. You don't observe any of the states, and it's more akin to a clustering. Right? You're trying to cluster the observations into these different states. And you're not trying to necessarily evaluate how well the HMM is classifying if you don't have any labels to evaluate its performance. And that is the most common thing we do in animal movement, in part because we put the sensors, the ecologists put the sensors on the animals, because then the animals can just kind of move around, they can roam, they can do whatever they want, and you don't have to follow them, which is the biggest thing. Right? And you can also do, semi-supervised, where some states are known, or supervised, all states are known. And that's typically to construct an HMM as a classifier. The nice thing about an HMM doing in a supervised fashion is that it takes into account the temporal dependence of the data and the likelihood that if at time t the state is in, say, state 2, then there's probability in the next time point that it's going to remain in state 2. So there's some persistence, right? Which is, if you use random forests or other machine learning algorithms, there is an assumption of independence. And state decoding in HMMs and extensions. Assigning an observation to a state is known as state decoding. And there's two common approaches. What's nice about STAN, I think it includes all three. Maybe.
It at least includes the local state decoding.
And I think the posterior draws as well. So there's local state decoding, you get the marginal probability of the states, and then you have global state decoding, which is the most likely state sequence that could have generated your data. Okay. And less common is it's quite easy to sample from the joint posterior distribution of the states to get sequences of states that could have generated your data. Right? So, figured, for me, it's always hard to see some mathematical object and know exactly what it does. So I'm going to show you some data. So say we have a 3-state hidden Markov model. Each state has its own normal distribution. So it has its own parameter values for that particular state. We can define the transition probability matrix so that the top left corner is the probability that, given that the, say, process is in state 1, it'll transition to state 1, and so on. And you can use the colors as the different states. So we have the gold state, the blue state, and the green state. So if you've never seen an HMM before, the idea is you can at least look at the data. What type of data does this model produce? And for me, I found that when I'm working in an interdisciplinary setting, especially with people who don't do a lot of math, I can say, you don't have to know what the model is exactly, but I can produce some data for you. Does your data look anything like this data? Right? And I love that I see a lot of heads just like, yes. Because we're not going to get anywhere if I'm just like, no, you have to understand there's this transition, there's a Markov chain. Now let me go back to basics, right? Like, no, you lose them. But you can show them some data. And so you have we can take a look at the time series. So the idea is that you have some persistence in, when we have gold observations, there's a cluster of gold observations. Then when we switch to blue for the first time, we don't remain there, we only remain there once. We switch to the green, and we have a few green observations at a time. Right? So that's the idea. And for animals, it's really the idea that once they start eating, as long as you have data collected at a proper temporal resolution, they're going to be eating for a while. If they fall asleep, or if they're resting, they're going to be resting for a while. So we want to take that into account as well. And if we just produce the histogram of the observations of the time series, we could see that we have these 3 different distributions. It looks like a finite mixture model because a hidden Markov model is just a dependent mixture model. It's going to have the same weights. There's going to have weights associated with the gold, the blue, and the green. And that's just if you had never seen a hidden Markov model before. Here's what it is, right? Here's some data, and here's what a histogram looks like. So my first HMM project, I'll say came about because, again, PhD student, shark obsessed, started Googling. And even before the Googling, I got onto Twitter. So I don't know the current state of academic Twitter right now. But back in the day, I just got on Twitter, I Googled search shark scientists, started looking for them, and started just following a whole bunch of shark scientists. And like, okay, cool, this is how I'm going to figure this out. And eventually, a professor who was at Iowa State as well, where I was doing my PhD, was going to do a sabbatical at St. Andrews. in Scotland, and that's where a huge number of ecological statisticians are. And for some reason, which is great for me, there was a shark scientist, Vianey, who just arrived as a postdoc and was like going around with his data to the different departments and is like, hey, I have this data. I like hidden Markov models. Will anyone please fit a hidden Markov model to my shark data, right? And so it all kind of came together. This professor knew that I was shark obsessed, that I love math. He's like, hey, there's a person in St. Andrews. I was like, yes, I've already found them. I already know who they are. He's like, if you can find your way to Scotland, you can stay with me and my wife in the house that we're renting, so we're on sabbatical, and I will let you come to the department with me. I was like, I'm there. So I showed up, shark obsessed, met Roland Langrock, who does hidden Markov models, met Vianey, who wanted someone to do something, and I said, I will do it for free. I don't need to sleep. Give me the shark data. So my first ever HMM project was looking at white shark movements in South Africa. This was in 2014. So this is one of the sharks, and this is the type of data they collected. And actually, the data isn't the position of the shark, it's the position of the boat following the shark. So there's a person who, for all these tracks, is on a boat and is just like going like this. And, okay, go further, okay, stop. The shark isn't moving. Okay, go. Right, left, no, move. Oh, stop. Shark is moving again, right? And they're trying to track these sharks to understand what's going on. And in part that there was this, and I don't know the state of the industry right now because of the killer whales, but there's a big tourism industry for these white sharks. If any of you have seen Shark Week on the Discovery Channel, like air jaws, these are these sharks. I was so excited. I was like, oh my God, I have like 10 years of air jaws that I've seen already ready to go. So what we wanted to notice here, and when I talk about HMMs and animal behaviors, we're not getting so deep into the shark was like, very tired that day and sluggish, so wasn't doing, it's very broad types of movements and behaviors. So there's sometimes when you see like a darker circle, and that's that the shark is kind of sticking around. It's hanging out in that area. And then others where you see more of a line, and that's the shark moving typically up and down the coast. They're not remaining in an area. Right? So these are really just the patterns that we're looking for in this data. There's sometimes where they stick around, they stay in certain areas, and they move around in other areas. And what they wanted to understand was, if there are boats chumming the waters, do the sharks come and hang out there? And how are their behaviors being modified by the tourism industry? Of course, it's hard to know if you don't have data before the tourism industry, but they wanted to get an idea. So often in animal movement, if you have data collected at regular intervals, because we're doing a discrete time, finite state hidden Markov model, they process the movement, the positions, into step lengths and turning angles. So you can use 2 consecutive positions to compute a distance, and then you use 3 positions to compute an angle. And then you have a bivariate response, which is the distance traveled and the angle traveled of the shark. Right? And as long as you have the first position, you can reconstruct the entire track using step lengths and turning angles. So you don't lose information, but they like to quantify movement in this term. So I was excited. This is my first ever research project, especially on sharks. So we did very basic things. It's a 2-state hidden Markov model, in part because we don't have any labels. Right? It's a sort of unsupervised thing. We're clustering the movements into different states, and we don't want to be so, okay, we know exactly what this behavior means, and these positions are very meaningful. It's kind of, they're traveling, they're sticking around. That was it. So one state was referred to as area-restricted search, and the other is traveling. And you can imagine the darker circles are the area-restricted search, and the lines are traveling. Right? So the idea is that in the data, the turning angles vary widely, and there's shorter step lengths, or shorter distances traveled when they're not leaving an area. And they're traveling, the turning angles are around 0, so it's more directed movement, and they travel longer distances. For the full model, what we wanted to do, we put covariates into the transition probability matrix, which can be done quite easily. You can do a lot of different transformations, but we used a multinomial logit link. So you can input a lot of covariates into the transition matrix, which means if, for example, we're interested in chum, how it affects their movement, and we incorporate it into the transition probability matrix, we might think that if there's an effect of chum, the sharks are more likely, when there is chum, to be in the area-restricted search movements patterns. That means that they're sticking around. Right? So as I explained this model, I hope all of you are thinking, I could have done that too. Right? Because again, you can all be shark statisticians if you'd like. And then we incorporated random effects, so-called discrete value random effects, that effectively cluster the time series into different patterns. We can talk about that later. They're not used so much. I think there's sort of a niche group that uses these discrete value random effects, and they love it, and they keep to it. And I'll get into my Bayesian section and say why I think it might not be a good idea. Right? So we did some state decoding. And for me, I loved it because I loved watching shark documentaries. And now the people that were on the TV shows, I just got to ask them questions. And then, which is fun, so I don't know about you, but in academia, we don't get that much validation. Right? It's more rejection than anything. It's never like a, oh man, you did so great. Oh, that was phenomenal. It's like, oh, okay, oh yeah, good job. You got the paper in JASA, fantastic. Okay, next paper. You're like, okay, that was short. Working in interdisciplinary settings is fun because you provide a lot of value and they get really excited. And then you get really excited because they're telling you all these really cool shark facts that you would not have gotten if you didn't know. And so one of the things I learned here is that female sharks and white whale sharks, they don't interact. Like they don't like to be in the same area. They're just like, please leave me alone. I'm going to be at the coast. And then the male sharks are down here. And if you look closely, these blue things indicate where they actually saw the sharks do a predation attempt. And sometimes they were leaping out of the water for that. And they're actually little shark fins. It's just the little things, you know? But if you look at this right panel, we do a close-up of one of the trajectories. And we have this black state, which is state 1, with the red dots we're indicating chum. And the black is clustering all the different movements that are, yeah?
What's chum?
Ah, thank you, yes. Chumming the waters means that they are cutting up fish and they're throwing it into the waters. So the sharks, are going to smell the blood, the fish, and they're trying to attract the sharks to them. Thank you. Yeah, so here we have this gray, which is the traveling state, which seem to cluster these observations pretty well to what we expected biologically. Okay? I also think that, let's see. Sorry, this one. My first paper, then I think I spent a year after this was published, waking up thinking I made a mistake. Something went wrong. These are not the results. But luckily, 10 years later or 8 years later, it seems to all be okay. So the next project I worked on actually started at the same time with these people, was shark accelerometer data. There's black tip reef, gray reef, oceanic white tip sharks. And a lot of the data that I work with is accelerometer data, which is basically records acceleration in 3 dimensions, so forward and back, left to right, and up and down. These devices can record, you can set them to like 40 hertz, so you're getting 40 observations per second. Juan Morales, who is a professor of statistical ecology at the University of Glasgow, has data on a flock of sheep, 8 months, and he's collected accelerometer data throughout. So if anyone wants to collaborate on some animal movement data, Juan Morales, University of Glasgow, has so much data. One thing, though, is because it's such a fine temporal resolution, we typically found that it would be really hard to fit parametric HMMs. So we went semi-parametric. And these are on the left-hand side what the histogram looks like. And the right-hand side, we use penalized splines to fit those density estimates. Okay. I realize I'm going very slow, so I'm going to speed up. And what we got for the ODBA is overall dynamic body acceleration. So you're removing the effect of gravity on the acceleration. And you're just looking at dynamic acceleration, which is you only produce it when you're actually moving. Right? So you're trying to subtract the effect of gravity. And we found we could sort of cluster things into 3 different states. And when you look at the dive profile, so sharks are negatively buoyant, the gold, this bottom, that seemed to correspond to less energy being used, was them going down. So they don't need to expend that much energy when they're going down. And then they expend different amounts of energy when they're maintaining their positions or when they're going out from a dive. So what I used to do is I was given the forward algorithm, direct maximization of the likelihood. People always talk, oh, there's local maxima. You know, it's just a thing. It's there, you have to deal with it, but you use different starting values. You find your global maxima, your global mode, and you conduct inference around the global mode. So the next up, going Bayesian. So by 2018, I had published a few shark papers. I was really excited, and I got to go to Galapagos. So this is actually the building behind me is an institute. So you can actually go to Galapagos, just work there during the day. There's whiteboards, beautiful meeting rooms, and then just go across the street to the beach and hang out with the seals. It's really amazing. And Alex Hearn does a lot of work on marine protected areas in Galapagos. So I was really excited, but at that point, I also started going Bayesian. And the reason I went Bayesian at that time was because I started discovering Stan. And actually, I discovered Hamiltonian Monte Carlo first. And the thing is, it looked exactly like the way I was doing frequentist inference. I could work with the likelihood directly. I didn't need to do this Gibbs, customize an MCMC. It was just my likelihood times my prior, get my posterior. It felt very similar. So I actually wrote my own pseudocode. It was not efficient. The gradients weren't great. But I was amazed at how quickly I could run Bayesian inference. And I thought, this is fantastic. I found a way to do Bayesian inference for hidden Markov models in a way that I've already been doing basically for frequentist inference. And it's not slow. People used to think, well, Bayesian is slow, so you do frequentist because it's fast. Right? So Charles mentioned that I'm an expert in hidden Markov models. And I don't think I'm an expert. I think I'm an expert in how they fail. I can fail to fit a hidden Markov model like no one else. And I will say, I think I wouldn't have gotten here if I hadn't gone Bayesian. Because as a frequentist, and again, you can do lots of types of uncertainty quantification with Bootstrap. You can look at your likelihood surface. You can take into account the modes. But the conventional thing was just looking at the inference around the global mode. As a Bayesian, I had taken courses and was told, well, you need R hats. You need your chains, you need these caterpillars to be one caterpillar, not multiple caterpillars. You need to expect certain things to know that you explored your posterior surface well for what you might want. And as a frequentist, I didn't really worry about that. And as a Bayesian, I was like, what's going on? So I feel like actually going Bayesian really made me think more about my models. And in reality, I realized I'm spending most of my time fitting misspecified hidden Markov models. And I think most of us, when we work on these different models, what we're really doing is we're always fitting misspecified models until we get to something that seems reasonable. So I needed to then go back and understand what happens when I fit a misspecified hidden Markov model. Because once I started seeing that my posterior chain, they were exploring different areas, I had multiple modes in my log posterior. And of course, back then, I could have started with parallel tempering or looked into something else, but I think those are really also hard to do well. And I wanted to understand just my HMM better. And so the choices we make when fitting an HMM in practice, you can fix the number of states, and you can select the forms of the state-dependent distributions. So I thought, well, okay, I get these multiple modes, and people talk about HMMs having local modes all the time in all their papers. And I started to try and understand, well, is this just what happens all the time? Even if it's correctly specified, I have enough data, my parameters are estimable, I pick reasonable priors, am I always going to end up with local modes? And so I started just simulating data, trying to understand what's happening. And actually, you're probably not really going to run into issues when you have enough data, when it's correctly specified, when everything's OK. And so I thought, well, if all these papers are talking about all these different modes, what are we ignoring? What's happening? So I said, like, well, I'm just going to fit a two-state hidden Markov model when the truth is a three-state. And this is really my life. My life is fitting hidden Markov models and then having multimodality. I've accepted it. I'm just trying to learn from it. There is once that I got this little jump across chains, across modes that I thought I was really excited about. But when I fit the incorrect hidden Markov model to a two-state to a three-state HMM, to data from a three-state, I get this. I get the sort of unnormalized log posterior. I get these different modes. And I did various simulations and ran like 15 chains for each one. The posterior draws for the second mean across 6 simulations. I was looking at them when it's around 0. I think that's when, because I also ordered the means. I think when it's 0, it sort of collapsed to one state. And in other cases, it was sort of taking averages between the mean of like state 2 and 3 or the mean of state 1 and 2. And it didn't quite know what to do. It's trying its best, right? So if I hadn't gone Bayesian, I wouldn't have thought that I was bad at fitting hidden Markov models. I would have thought I just need to have better schemes of coming up with initial values. But again, what am I ignoring then, right? Which has been sort of the big fundamental question that I've been asking myself. What are we ignoring when we don't quantify uncertainty around different modes? Or is it just that I've misspecified my hidden Markov model? And someone yesterday said to Marco, well, if you just increase complexity, that might just take care of it. And sometimes it does. Sometimes it makes it worse. We have a blue whale project, the one from yesterday. There are people trying to fit these models, and they're like, I found 20 different modes when I'm trying frequentist inference. And you're just like, OK, yeah, well, let's try to figure this one out, right? So one of the big things that I've been trying to do, and I really think I only got here because I went Bayesian, because I also took a course where simulation-based model assessment was emphasized, irrespective of how you do inference. Frequentist, Bayesian, fiducial, whatever you want. Simulation-based model assessment is really important and helpful. And for myself, I think if I hadn't gone Bayesian, I wouldn't have tried to really build this intuition. If I'm trying to fit a model, what does it look like when things go well? Because also, if you generate data from that same model, and it takes 5 hours to run, and then you fit your own data and it takes 10 hours to run, you might not think it's very slow. You're like, this is just how this is going to perform. So you get multimodal posteriors, but simulating data and fitting under misspecification helps me at least build intuition of how to do model building when things are seemingly going wrong, right? And it's really important for me, I think, and my students and others to understand when you get results, what went wrong, how can you use that information then to build your model, to make it better, to get better data, to do something different. Okay? And how different misspecifications manifest themselves in terms of the behavior, the likelihood, and the posterior distribution. Because in HMMs, as soon as you misspecify one thing, it's kind of over. So I did an oceanic white-tip shark example for a paper using a frequentist approach with the penalized blinds. So I did the full analysis. This is the paper where I did the full analysis using Stan. I used the Stan spline case study, which is fantastic, and a few other papers. And actually, this is the one time where I can say that there was such a significant difference in the computation time or fitting these models. In a frequentist approach, trying to figure out these penalty terms, and they were doing like this grid search, and it took days. In Stan, it took hours, and it was phenomenal. I was so happy, especially as people tell me like, oh, it's not going to be, you're not going to do great when you do Bayesian. It's going to go even slower. It was so cool. And this one, I got my multiple modes when I did a complete pooling across the sharks. So I would fit the same model to all the 4 different sharks. I got a multimodal posterior. My posterior was telling me, your sharks are behaving differently. They're not the same, which was really cool to see. So rather than look at my R hats of 20 and cry a little bit, I was like, oh, that's fantastic. What is it telling me about the ecology? It's telling me that my sharks behave differently. And it was very obvious that they might have behaved differently because we only had data for each shark for a few days. Sharks don't need to eat every day. Depending where they're going, sharks are really lazy. I don't know if you know. The one thing I discovered working with shark data, I thought it was going to be very exciting, is that they're very lazy. They don't expend energy if they don't have to. But I was really excited about this. So I've done a lot of interdisciplinary work using Stan, not using Stan. So manta rays in Mexico, sheep from Argentina. There's these baby snakes. So you look at the top right. They put a little red dot on their head, and we're tracking them. And then you're going to see Dr. Gangloff put a little Q. So then there's like, oh, how are they reacting? And we get their movements, and we're trying to understand how their movements are affected. There's these horn sharks with a little urchin, and you can see they have a little accelerometer tag on them. And the latest one was the bull shark collaboration in Mexico from a marine protected area. And then the fun thing is, once you can fit an HMM to Stan, you can fit all types of complex hidden Markov models. This one, people refer to this as sort of more of a hierarchical hidden Markov model. But a factorial hidden Markov model, a coupled hidden Markov model, a hierarchical hidden Markov model, you can always write them as a basic hidden Markov model. Transition matrix gets very big, right? But actually, you can fit all of these different types of models, semi-hidden Markov models, higher order hidden Markov models. And current shark projects, I figured I'd put this in here. And also, I use this photo for everything now. It was in North Carolina at the Collections Museum. I actually didn't realize I was wearing my Identify the Shark t-shirt. And I got the email like, hey, are we still good for the museum today? And I was like, well, yes, we are. Let's do this. And I got to hold a bunch of shark jaws. I was really excited. This is at North Carolina State University. But yeah, there's lots of data. I basically have too much shark data and not enough people who actually want to work on sharks. I keep telling students, like, I will send you to swim with the sharks. Come work with me, and somehow they don't want to.
Sounds like a threat.
I have taken Juan to Cabo Pulmon, Mexico, and they actually took him diving with the bull sharks to change out the acoustic receivers. So it's like, look, when I was applying for a job at Toronto, I said, look, I send my collaborators to the sharks. You should hire me. One of the newest ways that people are collecting data, which I think is really interesting, is video. And I think it opens a lot of possibilities, especially in terms of uncertainty quantification. So these are aggregations of leopard sharks. And you can see them swimming. And the idea is they want to understand how they aggregate and how they pick different temperatures in the landscape. They have data over the course of entire season and summer. And this is one of the newest types of data sets that we're working with. I actually had an undergrad student run INLA models. She's fantastic. And we're writing out the paper now. And then if you ever wanted to know the shark's point of view, so this is actually, the camera's on the shark. So this is after they put it, this is work by Vianey Papastamatiu. This is in Guadalupe Island. And right now we're analyzing this data. And there's another statistician who also told me, why aren't you using the camera video? Now here it comes. So you get these videos, you get this point of view of what the shark is seeing. Can this be another data stream? People have used it as qualitative information, but as a data stream, I was like, that's interesting. That would be a different likelihood. That would be, I don't know. But there's a lot of this type of data actually out there that people aren't really using. For me, I think as getting into the sort of Bayesian framework and getting into the simulation-based model assessments, personally, I'd love to get more into sort of simulation-based biological realism as a statistical model assessment. So how likely is it that my animal could have moved this way? One of my first talks with another ecologist ever was Stacy DeRuyter, who does the blue whale data. And she told me hidden Markov models are fantastic. They've been able to identify these different behaviors. They do the state decoding great. It's really useful. But they make no sense when you simulate the data. My whales are going to drown in 2 seconds. I was like, that's a low bar. We could probably put in whales need to breathe into these models. And so, right, regulating time underwater, energy expenditure, the physiological state. So I think for myself, this is something that in the next 10, 15 years, this is where I want to focus more of my energy when it comes to animal movement. And with Juan, we're putting together this model that tries to do a feedback between behavior and condition. And it's just like us. If we're not runners, and when you go try to run a marathon, you're not going to do well, right? But you run, your condition changes, your behavior affects your condition allows you to conduct different behaviors. We know this for ourselves, and we should know this also, how that might affect animals. And it's really, what is their physiological capacity to actually perform the behaviors that we're seeing them perform? Right? That's probably an important factor to keep in mind. But I promised you that if you did sharks, you could also become an astrostatistician. And here we are. So this is our preprint, detecting stellar flares in photometric data using hidden Markov models. Arturo Esquivel is one of my PhD students at the University of Toronto. Has done such a fantastic job. Really, who was talking about working at the National Lab and having the things, are they here? There's someone talking about having to give out, someone leaves all of a sudden and then someone else needs to take it on. So same thing happened with Arturo. This project was close to being finished, or we thought at the time, and the person left, ghosted us for a year. Like, what do we do? And Arturo came and basically saved the day and has run so many simulations. So the idea is that you have this observed brightness of a star. You have what's called a quasi-periodic trend, modeled by something called celerité. It's a Gaussian process. Basically, the star's brightness is going to fluctuate naturally. We also have a flaring channel because sometimes stars flare. Our sun flares, and there's stars that flare as well. But we don't know when it's in a flaring state or not. So what we did is sort of a proof of concept of, well, the student needs to learn hidden Markov models. Let's just work with some astronomy data and see how this goes. Apparently, it went very well. So we developed a 3-state HMM where the star was either in what's called a quiet state, it's not flaring, a firing state, or a decay state. So we have Y is a sum of a Gaussian process, which is modeling the quasi-periodic trend, and we overlaid a hidden Markov model on top of it as well to describe these flaring events. Okay. So we fix certain transitions, so it can't go from decay if it hadn't started firing to firing. Sorry, no, it can't go from, it needs to be quiet to then go firing to decay, and it can go back to firing, but there has to be a certain sequence of events that occurs. And this is what our model looks like on the top. This is real data, I believe, or I'll show you real data in a second. And there, that purple line is the quasi-periodic trend. And the black is the quiet state. And then we're trying to capture these flares, which is firing and decay. So the colored dots are the different states that we're capturing. So as far as we know, this really hasn't been done for stellar flares. What people typically do in astronomy is this sigma clipping. So they fit the celerity curve, and then they try to look at observations that are 3 standard deviations away. They sometimes even need to have 3 observations that are 3 standard deviations away in order to detect a flare in the time series. With an HMM, we're saying you can actually just at once get the full course of the flare, or an estimation. And what they'll do is they identify the flares, and then there's this iterative process where they're going back and forth and doing the sigma clipping. Okay. And one thing we weren't expecting is that when you fit the celerity with the HMM, the celerity looks very smooth because you're picking up what would make it deviate from this quasi-periodic trend with the HMM. So we did a whole bunch of simulations. We have this ground truth on the top. We found a part of the star that was not firing and injected these flares, which is the bottom. We have our proposed HMM. We have sigma clipping, and we're just doing some comparisons. We did some simulation results in terms of injected flare, the duration. Could we capture the entire duration of the flare? The sensitivity, and other metrics. And we can do the state decoding as well. So we can get uncertainty around the Viterbi decoding. Viterbi is what's the most likely state sequence. But because there's uncertainty of parameters, we propagate that to our Viterbi decoding as well. And what we're able to do is try to capture the entire course of the flare. And the reason why this is important is because this is how astronomers actually compute the amount of energy that a star is emitting. So you need to know where there is a flare, because there's an amount of energy being output from the star, and that's important. Okay. So I've done HMMs for sharks, and that's why I got involved with astronomers in my department as well. And somehow now we're doing astronomy. Now I need to get the astronomers over to the shark side. And we did kind of think that the flares look a little bit like shark fins, but we couldn't really come up with the acronym shark fin to fit this. And then the whole time series, you have the cyclical Gaussian process, and then you have the detected flares, and you have the uncertainty around it. We're getting the revisions back to the journal, but the archive paper is already up. So in summary, there's a few things. I think for myself, being at StamCon, is that being a Bayesian, or really just thinking about simulation-based model assessment, has made me a better statistician. Really trying to quantify uncertainty well, properly. And as a Bayesian, it's very, you got the prior, the likelihood, and the posterior. It's the same recipe. It's really nice. And it's made me really think more about my models, thinking about my specifications, what that means in terms of model fitting. And also, there's a lot of openness and interdisciplinary research. You don't have to be knowledgeable in multiple areas to really get into things. So if anyone wants to work on sharks, I'm here. Come chat, or astronomy. The GitHub is actually down here, Esquivel Arturo. You can rep their stand code. Everything is available there for you to use. You can reproduce the entire paper. So that's the last video. Can you see it yet? No.
Great. Thank you very much, Vianey. We have some time for questions now.
I have just a small technical question. When I was fitting this, so one of the things when I wrote the likelihood out for the HMMs in the user's guide, I was fitting the data from Move HMM, which I'd never seen before. I went to like ISAC and it was super cool.
Yeah.
All these models because they're really fun. How are you parameterizing the rotations? So like change in bearing.
The change in bearing. So how are we parameterizing it?
Because there's an issue, like all rotation, modeling rotations in 2 or 3D, that it wraps around. 0 and 2 pi are the same, so you
Yeah.
can get a multimodal distribution if you just naively model it as 0 to 2 pi.
Mhm.
So I was wondering if you were using like a unit vector kind of model for it. I've been meaning to do that for like 10 years and never tried it.
What Theo Michelot, who does Move HMM and Momentum, and I did is we transformed the angles onto the real space. So then you have an x and y coordinate that you can back transform. So we do inference for those x and y's on the real line. And I guess the idea is to put priors that kind of limits it to a certain area, but yeah.
You asked this really good question about, when you get multiple modes, is it only because of model specification? I never quite figured out what your answer was when you were doing the simulation studies.
Sometimes. I think, like someone mentioned yesterday, sometimes there's variation that you're not capturing. But if you have a finite mixture model, it's going to try to contort itself to saying, oh, they could be this, or it could be this configuration. So sometimes you can resolve it that way. Other times, you could have multiple modes because it's trying to fit a 3-state model, but it's entering a part of the parameter space where you effectively have a 2-state model, and then it has different combinations of the 2 possible states that it could be. Which that isn't really a model misspecification. It's just my guess there is you probably want to put the prior and say, okay, no, I want 3 distinct states in some way. I'm still not sure. Still exploring.
Sure.
Yeah.
I was wondering, I've seen HMM models quite a lot, but they always assume that the states are discrete. And kind of one thing I've been wondering is just why? Why not have continuous states? Didn't you end up with something a little bit like neural network or something in that case, where you just have a transition matrix? Would something like that work?
Yeah, you could have a continuous one. I think, to be honest, a lot of the people that are fitting HMMs that I know are frequentists. They probably don't want to deal with the integrals. But yeah, if you had a continuous state that could still somehow cluster patterns in a way that was biologically meaningful, continuous states could work well.
Did you mean continuous states in like continuous time measurements?
So
Or
like
just the state space is
just the
continuous?
state space. So
Yeah, 'cause
maybe
people
okay,
do
it's
that.
Yeah.
0.7 feeding and it's 0.1 sleeping or something.
It's just none of the efficient algorithms work anymore.
Yeah. Can't marginalize it out again.
But isn't it easier at least in Stan, to fit over continuous states? Because then you don't need to do any of the
You
integration.
just trade computer kind of fancy algorithm for way more parameters, I guess. That's
Okay, one last Euronext. Let's ask the last turn.
Comment on the previous one, so that's the state space model, and that's similar kind of marginalization algorithms for that as well. So,
The state space models?
yeah.
Yeah.
But related to the model modelity, I've been working with human models as well, and mostly on the frequent side, especially because of this model modality, and I just to sort of confirm the same thing that I've also noticed that it's often because of this model specification. But in my applied cases, we're usually dealing with life course trajectories of humans, and of course they are always misspecified because it's really a human models. So you end up with multimodality most of the time.
Yeah, and I've run into multimodality where I find it hard to fix the model because it can be misspecified because some animals have 3 states and others are only exhibiting 2 of those states. And there's always going to be at least one animal that does something different. You are guaranteed to have that one animal that's going to say, nah, I don't feel like it. And it messes up everything. So then it's hard to know how much to fine tune your models and things.